Good morning. Yesterday, we started the section 3.3. We were talking about how to analyze a function to figure out which interval the function is increasing or decreasing. So we're going to try it again with another example on the board. So here we have a function defined as x plus 1 over x. The question is to find all the values where the function is increasing. So basically, we're trying to determine the interval where the function is increasing. So if we find the derivative of the function, identify a critical point, we should be able to determine on the entire domain of the function, which section or which interval the function is increasing, which one is decreasing. So essentially, we are trying to figure out the increasing, decreasing property of the entire function. Right, so we're going to start as what we were doing yesterday. So the number one thing will be finding the derivative and then finding the critical point, and then using the critical point, we're going to determine interval. After determining the interval, for each interval, we're going to use a derivative to determine whether it's increasing or decreasing. So that will be the plan. Let me try to organize them so it won't be as messy at the time to try to write something on the board. It tends to be all crowded, partly because I try to write as big as possible. So here is our function. Okay, notice this function is different than the one we had yesterday. The example that we had yesterday, it was a polynomial, and a polynomial is well defined on the entire number line. So the interval that we start with is negative infinity to positive infinity. But this function has x plus 1 over x. X is well defined all the time. 1 over x is undefined when x equal to 0, because 1 divided by 0 is undefined. So because of this definition, the way the function is defined often causes us to determine a proper interval for us to start with. So in this case, because of that denominator, we know that x cannot be 0. So there, because if x equal to 0, it will be undefined. So the interval that we start with would be negative infinity to 0. And then you start over from 0 to positive infinity. We will be using round parentheses to indicate this is open, this is open, so 0 is not included in the interval that we're studying. I just ahead of time, I'm gonna identify that, because yesterday with a polynomial with negative infinity to positive infinity. Now today, because the function definition have that division in there, so we start with this. All right, we're gonna start with step 1, that is finding the critical point. I hope that you can start yourself, like if you were to find the derivative, what will be the derivative and what will be the critical point? Determine the critical. These critical points are going to be the separating point for the whole number line, for the whole interval. That's why we need to find the critical point. And remember, critical point is when the derivative equals 0 or undefined. So we have to find the derivative first. Now, to determine the derivative, we have to look at the original function. F of x is this. F of x is x plus 1 over x. So we're going to find the derivative one by one. The x has a derivative of 1. There's 1. Okay, and then other than that, we have 1 over x. 1 over x is x to the negative 1 power, right? So applying power rule, negative 1 goes to the front, the power negative 1 minus 1. Power goes to front, the power minus 1. So it's negative 1 times x to the negative 2 power. So that's at negative 1 x over x squared, because the negative 2 power means the division. So that's actually, look like this, x minus 1 over x squared. Try to think through the differentiation process. This again is applying derivative. We study extensively how to determine the derivative in chapter 2, but maybe we're still a little bit new to this. So occasionally you have to go back to the past, like the power rule, the product rule, the quotient rule, in order to figure out what will be the appropriate derivative. But the more we calculate, the more we practice, the better we get it. All right, so step 1, we're going to try to find the critical point. Now we have this. So let's try to find what kind of critical point do we have. And by definition, critical point, there are 2 types of critical point. One is when the derivative equal to 0, or when the derivative is undefined, B and E. Obviously, for the undefined point, we already have a candidate. You can see the denominator is 1 over x. Therefore, if x is equal to 0, it will be undefined. So the undefined point would be like 0. That's a critical point. Another one will be the derivative equal to 0. So we would also try to set the derivative equal to 0 and solve for the x1 minus x squared. And 1 minus 1 over x squared equal to 0. That's another kind of critical point. So we are trying to find all the necessary points we should determine along the entire number line. That will be the process of determining the interval. Once we have the interval, we now look at each interval, whether it's increasing or decreasing. So setting that equal to 0, now we have an equation to solve. Whenever we solve the equation, we try to identify how many variables that we had in the equation. So there's a minus, and there's an x squared in the denominator. So essentially, we will have one x value. And to solve this kind of equation, we'll try to any possible way to isolate the x. Since there's only one x, so we don't have to combine like terms. All we have to worry about is zoom in or isolate the x value. So what we can do is, right, we're going to have the 1 over x squared move to the right side of the equation. We have 1 equal to 1 over x squared. Okay, so that kind of looks like the one term on the left and one term on the right. To go forward, what do we do to solve the x? Well, can you guess the solution? I mean, it's not a long equation, it's a short equation. I wonder if I already see the solution. Just x equal to square root of 1. So x is positive. Could x be negative? Right? Square root of 1 is 1, right? So x equal to 1. Could x be negative 1? Yeah. Okay, so there's 2 solutions, x equal to 1 and negative 1. The process of solving, you can multiply both sides of the equation by the denominator, but by x squared. So multiply the left side with x squared, you have x squared. And then multiply the right side of the equation with x squared, you have 1. Because the x squared multiplied will cancel the denominator x squared, so that you get 1. Then x squared equal to 1, and that means x equal to 1, or x equal to negative 1. Basically, we take square root of both sides of the equation, and square root, we normally have 2 square roots for a positive number. So we have 2 answers. So now we finish the whole step 1. The step 1, we want to determine the critical point, and the number we find out, there's 1, there's negative 1, there's 0. So those are going to be the point that we're using to cut or to participate the number line. Okay, so we finished step 1. Let's try to make this true. Try to get more space. Okay, so we're going to move on to step 2. That is try to determine the interval. So we need to find out how many interval are we talking about in order to determine the increasing, decreasing interval. So I'm going to draw the number line. Right, we start with this number line. This is where we started because the denominator, so 0 is obviously undefined. So we have negative infinity to 0, and 0 is an empty spot. and then there's positive infinity. So I'm drawing out the number line based on the actual allowed value, and then I'm crossing out the x because I know the x is undefined. Because if x is there, the derivative is undefined, the original function is undefined, so we're gonna have to take out that x value there. And then you can see all the point that we find out. We have 0, we have 1, and we also have -1. So we're gonna mark out the according to the layout of the number line. Oh, we always has negative number on or small number on the left. So we have -1 and then 0 and then +1. So all the number that you find out in step 1 is now labeled in step 2. And you label them along the number line. Now you can see the entire number line is being separated into 1, 2, 3, 4. So the whole number line now become the 4 small interval, 4 sub-interval. Okay, about participating the line into intervals, do you have any question? Are we okay? Any questions? All right, so I'm gonna write them into intervals. So this is how we're gonna write it. You have -infinity, that's the left end of the original domain. We have -1. This is going to be, well, I think you can use a round bracket or square bracket because -1 is a valid point. And then we have -1 to 0. And that got to be open because we know 0 is undefined for the derivative and for the original. All right, and then a round bracket for 0, square bracket for 1 because 1 is included, and then 1 to positive infinity. Right, so I'm drawing that specifically when I identify that as 0, we would have a asymptote. We would have an undefined point. 0 is different than 1 or -1. 1 and -1 is, I'm writing bracket because it's continuous. The function is continuous from -infinity to 0. And then at 0, you're going to have an asymptote. That's why 0 is undefined because at 0, it's going to go up or down to infinity. And then again, start 0, undefined 0, and then 1. At 1 is continuous, and you keep going to cos infinity. Just want to explain the differences of the way we label our interval. Right, that's step 2. We now have 4 interval, and you can see why some of them are brackets, some of them are rounded, and it's they really have their individual meaning of it. All right, that's our step 2. Let's move on to step 3. In step 3, we're going to try to determine increasing or decreasing. All right, in step 3, we want to know if the function is if every interval, are they increasing or are they decreasing? That's question mark. So we have to do that for every interval. We need to know whether every interval is increasing or decreasing. Start with the first interval. Try to label them. I guess I should write step 3 down here. All right, so for example, the first interval, right? The first interval is from -infinity to -1. The entire interval is either increasing or decreasing. It cannot be both because whenever you turn from increasing to decreasing, you have a critical point, but we don't have any critical point in there. Therefore, the increasing, decreasing behavior are not going to change. Therefore, you only need 1 point to know if it's increasing or decreasing. So we pick any point in that interval. For example, we can pick -2. So let's calculate. Remember, you determine increasing, decreasing using the derivative. So we're going to find the derivative at -2. Because -2 is one of the number in that interval. So this is a calculation. We want to know increasing, decreasing. The first derivative is how we determine increasing and decreasing. So this calculation, you see the prime notation, you have to calculate using your derivative function, not the original function. So far we have not calculated any y values. We're calculating y prime, we're calculating derivative. So put the -2 into the derivative function. That's our derivative function. So we're gonna put 1 minus 1 over -2 squared. -2 squared is actually 4. So it's actually 3/4. Okay, now 3/4 is a positive number. If the derivative is taking a positive number, the function is increasing. So we know on this interval, on this one, it's increasing. So increasing here. First interval is increasing. And then second interval. The second interval is this one, -1 to 0. So on that interval, we also need to know if it's increasing or decreasing. But we have to pick a random number. I'm going to pick -1/2. So we're going to calculate this f prime of -1/2. To do that calculation is going to be 1 minus 1 over -1/2 square. If you square negative number, it becomes positive number. So it's -1/2 square is +1/4. 1 divided by +1/4 is 4. So this is actually 1 minus 4. Now 1 minus 4 is -3. Because this is negative, you can use your calculator, of course. I was just doing it so it's more visible in the recording. And you can pull out your calculator, do 1 divided 1 over parentheses 1 over 4 parentheses. So the division of fraction inside the fraction, you need to use a pair of parentheses to protect the operation if you're doing it with your calculator. So anyway, negative number. So we have a decreasing function on this interval. So on this interval is decreasing. Function behavior is decreasing. So I'm using down arrow for decreasing, up arrow for increasing. And then this decreasing is slightly different than this one because that one is connected and this one is not. It's a down decreasing without bound. So visually it should like this. It's kind of like increasing and decreasing, because here we have an invisible wall at 0. So 0 become a asymptote there. Trying to explain the differences between the decreasing and decreasing. This 0 is a discontinuity. Actually, it's an infinite discontinuity. That's why behavior like that. All right, and then start with the next interval. We have 0 to 1. 0 to 1, we also need to pick our number. We're going to use the derivative to determine whether increasing or decreasing. We calculate f prime of +1/2. But +1/2, when you square it, is +1/4. So similar calculation, this is also -3. So it is also decreasing. So it looks like this. I should try to make it more visible. This is not visible like this way. But remember, it's continuous at 1, but then this is going to go down from infinity. So look like this. Okay, that's what I think is the behavior. It decreasing up until the number 1. A 1, I don't know the y value. So I have the x value that equal to 1. It's the 1. Just try to you can after you study the increasing, decreasing, you start seeing the behavior of the function in a more visible way. In your head, you can imagine that picture. Because now you know more about the increasing, decreasing. The last interval I have already drawn over here. I think it will be increasing because we're taking on a larger number. For example, we should try 2. So you calculate f prime of 2. 2 is a number in this interval. So if we calculate it, it's going to take on 1 minus 1 over 4, which of course will be 3 over 4. And that's positive. That's why this part is increasing. That's why I'm drawing that increasing part of the curve. So you can see it looks really different the way we draw it on the left. We only study increasing, decreasing. We don't know what was the y value. On the right, I'm trying to imagine. You can see at 1 or -1, those number, the y value is very important because y value will affect whether the curve is up or down. I think the way I draw it may not be right because I should pull this right side a little bit up and the downside a little bit down. So it should like this. I feel like maybe the height, since I didn't calculate the y value, and as you can see, when we try to calculate maximum, minimum in the first section, we do calculate y value. And right now, we only calculate the derivative, and therefore we don't know the height. I think it's supposed to be this way. It should be a little bit higher there. Because underneath it, we have the 1, like the 1, that's x, the x function. So y equal to x would be like over here, the line that goes y equal to x. is there. So it's y equal to x plus the 1 over x part. That's why we have a slant asymptote to the curve. And this is, it doesn't serve it right, but it's a really rough sketch, and at least it gives us some idea for how the function behave. And we're pretty clear about the increasing, decreasing now. But to be sure, you can also graph it, of course. The main purpose of this exercise is to grow or train the skill on how are we going to know the increasing, decreasing behavior of a function using the calculus method. So this is how it looks like when you graph it, and you can see that's the 1, and that's the -1 and 1. So it goes increasing and decreasing, and then decreasing, then increasing. It has a 0 as the asymptote right in the middle. So it's really important to realize that 0 play a key role in the whole graphing of the function. So we have the increasing, then decreasing, decreasing, and then increasing. So you kind of see the increasing interval now. Now we're going to go back and actually answer the Flickr question. I hope that we have a pretty good idea on how do we use the derivative as a method or as a information tool to understand the increasing, decreasing of the function. Okay. And then pull up the scanner so I can scan your solutions. Okay, so the answer should be it's this one, right? But you didn't. Okay. I think one of the edge is in your finger. Okay, cool. I think all of our answer has been scanned. Well, if you haven't really submit your answer and you're online, let me know if you are missing the link. All right, we identify the increasing interval, right? And then over here you see the interval that is increasing, kind of. Like this is increasing, right? And then that one is increasing. And then the other two interval is decreasing. So over here in this picture, we are specifically identified or labeled out the increasing or decreasing on every interval. And there are 4 of them, 4 intervals. So the increasing interval is -infinity to -1, and then +1 to +infinity. And then you look at the choices. The set of value for which the function is increasing is, see, it should be A. If you answered it wrong the first time, and I hope that you can review all the steps and have a answer, collective answer. Let me try to make it smaller so that we see the whole picture. So I used to just think of it as 3 steps. Step 1, you figure out all the key number you need to put on your number line. So step 1 is determine the critical point, including the undefined point. And step 2, you're going to label all those points here and try to find a way to differentiate them. The number that is undefined is different than the number that is continuous. So the one that derivative equal to 0 is different than the one that derivative is undefined. And then once we have that, the number line is being separated into 4 parts, and then we now have the interval. Step 3 will be determining the increasing, decreasing for every interval. And how do we determine if it's increasing or decreasing? We determine that by calculating a variable number of those derivative. And it doesn't have to be those number I choose. For example, you can do f prime of 3 or f prime of -4 for the first and last interval. You can use that as a number. I picked the easy number, just so the calculation won't be too difficult. But for the determination of increasing, decreasing, the choice is not unique. So you can decide which number you do calculate yourself. I hope that you all had a chance to upload your answers. Dylan, are you there? The answer is supposed to be A. I sound like I made it pretty clear. Dylan, are you online? We're trying to wait for all students to submit their answers. Anyone that's missing your clicker link? I don't see Alexis or Laura. Like a student attending online. 11, and the answer submitted is 12. So we're missing one. Dylan, are you online? Okay, so that would be, I guess, okay. Do you have any homework question you want to mention before we move on? Yes.
I have a question about this problem. How were you able to figure out that 0 was undefined?
Oh, you see the 1 over x. When x equal to 0, 1 over x will be undefined. So that it's the original interval is from the definition of the function. So definition of the original function causes us to identify that x equal to 0 will be undefined for the original function. And then if you look at the derivative that we calculated, the derivative is 1 minus 1 over x squared. And x equal to 0 would also be undefined for the derivative. So it's undefined for the original function and undefined for the derivative function. That's why we mark out 0 specifically to know that it won't be, we will not have a graph over it because it's an asymptote, it's undefined. I hope that kind of makes sense. Normally the undefined point would be called the definition. So if the function is a polynomial, it will be always well defined. There is no undefined point. If we have division by 0 always have the. Well, if we have division, we should try to find a common factor. After canceling any common factor in the irreducible fraction, the denominator equal to 0 is how we determine the undefined point and the asymptote. And other than that, if we have logarithm and a logarithm of 0 would be undefined. And then if we have a square root, root of negative number is undefined. So those are numbers that we would exclude from our domain. So once we see other kind of function, we'll talk about it. Any other questions, homework?
I have one about number 7 on the homework.
7 on 3 point.
Oh, 3.2.
3.2, number 7. Yeah, we haven't really practiced a lot of question on 3.2. We practiced the first 1 or 2, and then we stopped. Gonna wait for you guys to have such an amount of practice. So 3.2, number 7. Next question.
Yeah, so I went all the way through because mine was similar to that, but it was to the -8th power. And it was on the interval 1 to 10.
Okay.
And when I got through to it, because when you multiply 10 by the -8th power, it becomes like a super tiny number, right?
I see.
So it kind of, I don't know if I did it wrong or what, but I did it like 3 or 4 times and I just kept getting super tiny numbers that were super hard
Okay.
to divide.
If you don't mind, can I show your question instead? Because it looks like my number has the -2 power doesn't make it small. If you have -10 power, I think it's because the question was random, and that may be a special case. So let me pull up your question. That one, is that yours?
Yes.
Do you have -8?
Yes.
Okay, so let's work out this example. This is mean value theorem. So the step will be calculating the mean value and then calculate the derivative and then set it equal to the original function. So let's calculate the mean value first. Okay, I'm going to type since my writing is the mean value. Okay. So the mean value would equal to And we have our interval, so we would calculate f of 10 minus f of 1 divided by 10 minus 1. So the term mean value is a slope calculation. So we calculate subtract the x value in the denominator, subtract the y value in the numerator, but the y value is not given. So we have to calculate the y value. So let's calculate f of 1 is equal to, this is our function f. So f1 equal to 1 to the negative a power, which is actually equal to 1, and f of 10, like you said, is going to be 10 to the negative a power. It's really a small number. I'd rather keep it in this form because if you write it into decimal, it would be 0.000000001, another 0, and then 8. So that's how the representation in decimal. So it's not as convenient and not as clear writing into a negative power. So let's keep it in the form of 10 to the negative a power instead. Well, it's 1, right? It's not 8. I was wrong. It's 0.00001. It's the 8 represent the number 0, but it doesn't represent another number. I have a habit to write whatever I was looking at. So because I was writing, my eye was looking at 8, so I write 8. Sorry, I copy the wrong number all the time. So now that's the numerator. So a numerator would look like this. This is 10 to the negative 8 minus 1 over, and 10 minus 1 is 9. So the denominator equal to 9. So that's the mean value. So that would be step 1. And step 1, you determine the mean value. And step 2, you determine the derivative, and derivative is equal to, we apply power rule, we bring the negative 8 to the front, and the power has to minus 1, but we have a negative power. So if you have negative 8 minus 1, it's going to be negative 9. So that's our derivative, and that's our step 2. And step 3 is we're going to set it equal. Basically mean value, so you're saying one of those number at prime C equal to the mean value. So we have the mean value, we have the derivative, all we have to do is set it equal. So it looks like this. So this is our equation. We have our derivative, negative 8 x to the power negative 9, which equal to 10 to the negative 8 power minus 1 over 9. Okay, so solving for the C means we have to solve the x from the whole equation. Are we okay right now? So I would prefer, you can see this also is that kind of equation that you have only one of the x value. And then all you have to do is get rid of everything else. Are you with me? Right, so number one thing we would prefer is the exponential function is a tighter relation than multiplication. So we would get rid of the negative 8 first, and then remove the negative 9. So how do we get rid of the negative 8? How are you going to remove it? It depends on how it's combined. Originally, it was combined through multiplication, so you can remove it by division. So we divide by negative 8. Therefore, we also have to divide negative 8 on this side. So we divide a negative 8 on the left and divide negative 8 on the right. So you kind of look at like having an actual denominator of negative 8 on both sides of the equation. So then the negative 8 will be canceled. After we've done that, the left side will become x to the negative 9 power. Okay, which equal to 10 to the negative 8 minus 1 over negative 72. I would try to combine anything that's easy to combine. Anything that is hard to combine, I tend to leave it the way it is. For example, the numerator is 0.001 minus 1. You can calculate it, and then it causes you to have a long decimal in the numerator. So I kept it in that form. All right, next thing is we wish to remove the negative 9 power. The way we remove negative 9 power, you use power to remove power. So if the power equal to 1, x to the power 1 would be x, right? If you get x by itself, that means you're going to revert the power to a 1. So you get a power equal to 1, the power should multiply power. That's why power get rid of power. Or another way of saying the power function will be removed by a root function, and root function is fractional power. So what we need here is a fraction power. The fraction has to be the reciprocal of the exponent. So for the -9 power, you need -1/9 power. So we are raising both sides of the equation to the power of -1/9. Okay, so both sides we remove it to -1/9 power. Okay, after we've done that, you can see on the left side of the equation, -9 multiplied by -1/9 is 1. That means x has a power of 1, which is the same as x. So the left side is x. The right side, the calculation looks a little bit odd. If it's kind of cumbersome to check, you can switch the order because normally we take root of a positive number. So we can turn the denominator to a positive 72. We also turn the numerator to a 1 minus 10 to the -8. That way, at least we don't have those awkward negative signs raised to the -1/9 power. Also kind of goes with the value of the number because 1 is a larger number. The 10 to the -8 is a super small number. So normally we take a large number minus small number rather than minus big number. So that should be the solution for your question. And then the rest is you put it into a calculator. I would try to put it in here to say if this can be your calculator. So we're raising this fraction to a -1/9 power. So let me try to make this larger so you can see it. The power is a -1/9. That would be power. In the inside the parentheses is a division, and the denominator is 72. So we have divided by 72, and we have to what with the numerator is 1 minus 10 to the -8. So I'm trying to protect the order of operations since there's subtraction. 1 minus 10 to the power of -8, and that should have the calculation down properly. That's the answer. If you and you can see the calculation is being carry out the calculation using the. Well, I didn't touch anything; it moved by itself. But that's what we are writing, right? That's what we intend to calculate. You can also put it into your calculator to check if that number agrees. But this is me checking it. It won't change you have to put it in yourself. You can see down there, there's still has 0% there. But you have to go home and sit down and enter the answer yourself. I hope that kind of explains. Right, so sometimes it's tricky. Sometimes it's a way to maintain your thought process so nothing get overwhelmed by the number itself. Sometimes just by looking at those huge amount of super small number, it causes us to get a little bit annoyed by the difficulty to handle them. So I would prefer to keep in a format that is slightly difficult, but not too difficult to the point it's hard to handle. That's why I tend to keep the raw calculation rather than have the decimal number. Any other questions? If you're online, do you have any question you want to ask before we move on to 3.3 for further topic? Any question? Right. If you have your mic on, it will be easier to speak through the mic because it will be faster than typing. But typing is fine if you don't want to speak loudly.
So did the negative go away just because you raised it to the -1/9?
This is the fraction. The denominator is -72. The numerator is a small number -1. So that's also negative. So we multiply negative to both denominator and the numerator. Then the -72 become +72. The numerator also gets switched. So switch to the opposite. If the numerator and denominator both multiply by -1, they maintain the value of the fraction. I hope that kind of makes sense. The originally 10 to the -a-1 is a negative number. -7 2 is a negative number. So negative divided by negative is a positive number. That was in the second to the last row. In the last row, I switched it to 72 is a positive number, 1 minus 10 to the negative 8 is also a positive number. So it's positive divided by positive, which also is a positive number. So it's all about keeping the same value, but losing a little bit of the complexity of the representation. They're the same value. All we did is change out the negative sign. I hope that kind of explains. Is that what you were asking?
Yes, I think so. I just got confused because it was a exponent.
Yeah, it's an exponential calculation. Basically, the exponential calculation, if you have a negative exponent and that just making it into a division. So the negative sign means division and the fraction means root calculation. So none of them are changing the value. So basically we are raising a fraction to a power, to a negative power. But the original understanding or treatment of the fraction is still the same. So inside is a fraction that we're handling, and most of the rules about fraction is still apply. So we're changing the fractions format for the ease of representation. Any other questions? Any other questions? So this is the example from the homework. Let's try to continue where we started out yesterday with section 3.3. Mainly on 3.3, we're going over increasing and decreasing behavior. We've done a couple of examples, but I believe we haven't really finished everything. So the title of section 3.3 is increasing and decreasing function. And the most fundamental idea is that derivative is equal to a positive number, then the function is increasing. If the derivative is a negative number, then the function is decreasing. So first we defined the increasing, decreasing behavior of the function through the relation between x value and y value. Basically, if the x value is increasing, like a to b is bigger, so the x value is increasing, then the y value is also increasing, f of a is less than f of b. That means increase and increasing matches, they're all changing in the same direction. That is when the function is increasing. On the other hand, if x value is getting bigger, like a is less than b, so b is bigger, then the b actually is smaller than a. So x value gets bigger, y value gets smaller. So they are changing to opposite direction. That means the function is decreasing. So that's how I interpret it. In a way, all you have to do is the two pair of inequality, are they all are trending in the same direction, or are they trending into opposite directions? You see in the notation wise, and we're just trying to form a good definition, a good understanding of the increasing, decreasing behavior. So you can see here, this is less than, and then less than, and that's when they are all going to the same direction. So they have increasing. Or you can also define that if A is bigger than B, then F of A is bigger than F of B. So as long as they're all in the same direction, they're all fine. Different book may define them the same way, different way, but then the fundamental idea is that they all have to turn into the same direction. Inequality for the X value and the inequality for the Y value are all turning in the same way, and that's increasing. Now, decreasing in the opposite way, decreasing, you can see that when x is a less than b, so x value. Now, f of a, f of b, those are the y value. So when the x value is increasing, the y value actually is decreasing. You see, this and this is in opposite direction. That's a typical behavior of decreasing. You can try other ways. If this is like bigger and this is actually smaller, that's also same, like consistent with the definition for decreasing. So I hope that kind of makes sense. I kind of feel like, even though this is very conceptual, but understanding it, the more you understand it, the better for future study. That is the definition for increasing and decreasing of the definition of the function. And then we had test for increasing, decreasing. If the derivative is positive, then the function definitely is increasing. If the derivative is negative, then the function will be decreasing. If the derivative equal to 0, then the function is constant. So these are for when the function is the same value on the entire interval. I mean, we mean positive for all the number, therefore it's increasing for all the number in the interval, or negative for all the C, and therefore it's decreasing for all the C, equal to 0 for all the C in AB. That of course is constant for all the AB. So these are not for a single point, this is for the entire interval. And then we mentioned how do we determine interval of increasing and interval of decreasing for the function. And we went through these 3 steps. Step 1, you find out all the critical point. Step 2, you find out the interval. Step 3, for every interval, you're going to pick a number to make a test and use those tests to determine increasing and decreasing. And that's something we've been following yesterday and today. This is the example that we did yesterday. And then this is where we stopped. Okay, let's talk about the first derivative test. The title is called first derivative test. So you can imagine there is a second derivative test. And therefore we gotta watch out for those. Both of them serve the same purposes. That is, we have to have a firm understanding of all the possible relative minimum and relative maximum. The first derivative test uses the first derivative. The second derivative that we'll be learning later will be applying the second derivative. The second derivative is a derivative of the first derivative. So of course, a little bit more complex, but normally you gain a little, you lose a little. If you have one part that become more complex, and then the application part must be a little bit easier. So there's a trade-off in between those. All right, let's first focus on the first derivative test. Number 1, you have to have your first derivative. F prime is the first derivative. It has to be well defined. So when we see function f is differentiable on I, we mean the function has the first derivative. Suppose C is a critical number in the set, and therefore C will be very important. If C is a critical number, then the derivative as C is either equal to 0 or undefined. So C must be one of those special number. Now we need to know whether C is a maximum or minimum, or is neither of those two. So 1, 2, 3 are trying to analyze the derivative to determine as C what's happening. Number 1, let me try to copy this over so I can write on it. All right. So the first scenario is talking about the SC. Let's see. All right, let's see if the sign of the derivative switch from positive to negative. That means the derivative is positive. That's increasing. I guess we don't know that. We don't need a horizontal line, right? So positive means that the function is increasing. Negative means it's decreasing. Okay, and right in the middle is where the C is. So if as turn from positive to negative, and f prime is C, which is the C, the value at C. So here we have C, f of C. F of C is the y value. Then that y value must be a local relative maximum. So that's the first scenario. So that means specifically as C, the derivative are switching signs. To switch from positive to negative, so it's increasing then decreasing. As C, we have the maximum. Second scenario saying, suppose the sign of the derivative switch from negative to positive. So what does it mean? If it's negative, then it's decreasing. If it's positive, then it's increasing. So that means the function's graph switch from decreasing to increasing, of course, at prime C, which is right over here. And then C is the x value, f of C is the y value. Then f of C has to be a relative minimum. And you can see from the graph that in between the decreasing and increasing interval, you have a special critical point where you have the minimum. Lastly, the third scenario is if the sign of f of A does not change as C, then f of C is not a relative extremum. So it's not a relative minimum or a relative maximum. what does it mean? I mean, sometimes the function had a critical point, but it didn't change signs. For example, could be like this. It went decreasing, and then you have like a slightly horizontal situation, but then it went down again, right? So there's a C. So at C, you seem to have a horizontal tangent line. The line seems to curve steady for a minute, and then it went down again. So this is decreasing, then decreasing. Or another situation will be it went up and then went up. Right in the middle is where you have your C. So at C, we have a derivative that equals 0. So you can visually try to put a tangent line that's horizontal, but we have a horizontal tangent line that doesn't guarantee we have a local extreme. So this is when the f of C is not a relative minimum or relative maximum. If it did not change, then it's consistently decreasing or increasing, and therefore we don't have a relative extremum. Any question? I hope that kind of makes sense. Does that make sense? All right, so this is the first derivative test, meaning that we are testing or determining whether we have a relative maximum or relative minimum using the sign, using around the C, what happened to the derivative? Is it positive or negative? Or is it negative, positive? Or is it always negative or always positive? Those are 4 different situations. Among the 4 different situations, one of them, if it switch from positive to negative, you have a maximum. If it switch from the decreasing to negative to positive, you have a local minimum. And if it's negative and then negative, that it's decreasing the whole time. If it's positive, then it's also always be increasing, right? So that's the first derivative test. It tends to give us a good idea for the increasing, decreasing behavior of any function. And that's how we determine maximum or minimum. And now, normally, once you understand increasing behavior and decreasing behavior of the function, you pretty much are quite sure of what's going on. All right, we're gonna try that again. And this is another example. It's similar to the one that we just did. And we have a division. Whenever we have a division, we have to watch out for that number that makes the derivative equal to 0, because you have a natural point where it's undefined. We will have an asymptote at 1. If x minus 1 equals 0, then x equal to 1. So you kind of have to immediately take out the number 1 before you can do anything else. And that's called the domain, like the implied domain of the function. The function's definition calls us to identify problem point and identify the domain of the function before we can do any other calculus procedure. So let's copy this question over, and we're gonna do the first derivative test. Okay, so let's see, because we got this denominator, if x minus 1 equal to 0, then add 1 to both sides of the equation, then x equal to 1. It's by adding 1. So if x equal to 1, then 1 minus 1 equal to 0, which will cause the whole function to be undefined. So we realize we cannot let it equal to 1. So then x equal to 1 will be forbidden point for the x value. So we will allow any x value except 1. So that this is the interval x is less than 1. All right, and then we can have 1 to infinity. 1 to infinity is the same thing as saying x is bigger than 1. These are just try different interval notation representing those inequality. Okay. So we're gonna start with that interval as we were trying to determine the interval for the increasing and decreasing. So find the interval for which the function is increasing and decreasing, and then use the first derivative test to determine the relative extremum. So we want to, not only do we want to find increasing, decreasing, we also want to find whether we have a relative minimum or a relative maximum. All right, we're going to follow the steps that we were talking about. Basically, if those 3 steps, step 1, we're going to try to determine critical point. Points. And for that, you will have to find the derivative. Critical point is determined by the derivative equal to 0, or when the derivative does not exist. So those are what we're searching for. So in order to do whichever we're doing, we need to find f prime first. So let's calculate the derivative first. Because the structure of the original function, we need to do a quotient rule. Follow the quotient rule. Try to move this up a little because I'm losing some spaces. So it's going to be a division. The derivative of a division, of course, is another division. The denominator is squared. And let's repeat the quotient rule. According to a quotient rule, you have one function divided by another function. The derivative of this is equal to the denominator has to be squared. And numerator have a similar effect format to the product rule. F prime g minus f g prime. Okay, so follow that format, denominator has to be squared and numerator have to be differentiated. So x squared plus 3 have to be differentiated, and you're going to have 2x. And then multiplied by the denominator. Minus, this time we're going to keep the numerator. X squared plus 3 is our f. And we're differentiating the denominator, which is equal to 1. And whenever it's 1, we don't have to write it. That's applying the quotient rule. Any question? Are we okay? All right, so we're going to try to clean up a little, try to combine the terms. In the numerator, distribute the term outside the parentheses. We have 2x squared minus 2x, and then minus x squared. It's minus outside the parentheses, so it's minus 3. And then the denominator should say x minus 1 squared. So now we have x minus 1 squared. And the numerator, we have x squared minus 2x squared minus x squared, and then minus 2x, and then minus 3. Okay. So now we have a fraction. We need to know when would this be undefined and when would it be equal to 0. Remember, when you have a fraction, the fraction can only equal to 0 if the numerator equal to 0. So numerator equal to 0 is when the derivative equal to 0. Denominator equal to 0 is when it's undefined. But the thing is, we have already taken out the 1 when we're talking about domain. So x equal to 1 is already not in the consideration. So we don't have to focus on the undefined point since it's already taken out of the domain. So we only have to worry about the numerator equal to 0.
That's the, wouldn't
Yes.
that be plus 3 because we're subtracting negative.
Minus,
I didn't know. Just kidding. I read it wrong.
okay, yeah, so you have a minus 3 over there?
Mm-hmm.
Okay.
And so I had a plus 3.
Uh-huh.
I think I read.
But as long as we all kind of pay attention, follow through, but thank you. All right, so this is applying quotient rule. Let me get rid of the side so it won't be combined or mixed up with the floor. So we're gonna make the derivative, make the numerator equal to 0, just to solve the critical point. So we have x squared minus 2x minus 3 equal to 0. Now denominator cannot equal to 0 because you see we are taking the 1 out of the domain, and that should be marked out on the number line. But as long as we did mark out the number line, so this we don't have to worry about it. But if you worry about the undefined point, you can also mark it down like x cannot equal 1. That way the undefined point will be considered when you draw your number line. And it's still something we shouldn't forget, but we don't have to worry about it since we did mark it down. And then let's try to solve the numerator equal to 0. It looks like something we can factor, right? 3 times 1. And negative 3 times 1 is negative 2. So we have x minus 3 and x plus 1. It looks like something that we can factor. You can follow this to confirm x times x is x squared, negative 3 times 1 is negative 3, and then negative 3x, positive 1x combined is negative 2x. That kind of confirms the process factoring is correct. The factor allows us to write it into two separate equation, x minus 3 equal to 0, and x plus 1 equal to 0. Solving these two equations, we have x equals 3, and then x equal to -1. So these are the key points that we find out from step 1 or the original domain. It also allows you to realize that 1 is the number that we should mark out on the number line. And that's kind of a couple preparation that we need to do in order to determine the proper intervals. The one thing we should avoid is missing out some of the key number when we're constructing the number line. So step 2 is we are trying to determine the interval. Try to find out the intervals. This is done by drawing the number line and then mark out the necessary points. So we have a number line, and then you can see the original idea is through the definition, visualize 1 is right in the middle. At 1, we should have the empty points because 1 is undefined, and also because here, see the 1 is undefined, right? And then we find out 2 other points. Other than 1, we have 3. Also have a -1 in that order. -1 is smaller than 1, is smaller than 3. So -1 smallest, and then the 1, and then the 3. So all the 3 number we find out in step 1, you have to clearly follow that order and mark them out on your number line. Now we have our interval. It's the negative infinity on the left and then positive infinity on the right. So you can see we have 3 special points, 3 special points that separate the number line into 4 intervals. Let's write those intervals out. So you have negative infinity to -1. -1 is a continuous point, and -1 is okay. So we have -1 with a bracket, and then we have -1 to 1. But remember, 1 has to be a round bracket because if x equal to 1, it would be undefined. And then we have 1 to 3, and 3 is if x equal to 3, the derivative this will equal to 0, but equal to 0 is fine. It only just gonna mean that maybe a local maximum, a local mean, right? And then start from 3 to positive infinity. So we're writing, follow the entire number line in that order. Remember, interval is part of the number line. So we follow the number line, write out all the interval properly. So now we have our 4 interval. For every interval, we want to know increasing, decreasing. So that's our step 3. And we're going to try to calculate some derivative in order to know if it's increasing or decreasing. So step 3, we want to know whether the function every interval, we want to know it's increasing or decreasing. Notation. I mean, writing the word increasing, decreasing is long. So in class, sometimes I resort to those arrows, so it's easier and save time. Okay, so let's look at the first interval. You want to take a number in that interval in order to see, to tell whether it's increasing or decreasing. And it looks very similar to what we've done before. So let me calculate the derivative value at -2. So that's the next number after the -1. That's why I normally pick a number. That's won't be too big because if it's too big, my calculation will be hard. So what are we doing? I would probably pop it into, see the numerator is the same as this. So I'm going to write calculation f prime of x is equal to, those are the f prime of x calculation. They're all equal, but of course I want to pick one for that's easy for calculation. So I'll do x minus 3 times x plus 1 divided by x minus 1 squared. So I'm going to do this calculation. For example, for -2, we will have numerator is -2 minus 3, that was -5. And then -2 plus 1 is -1. -5 times -1 is multiplication. That makes it +5. Denominator is going to be -2 minus 1 squared. And that's actually a -3 squared. It's 9. So it's 5/9. So it's positive. If it's positive, that means it's increasing. So on the first interval, we got an increasing behavior. Any question? right? Second interval, you can see there's -1, there's 1, right? Between the negative number and positive number, there's always 0. So we would try to calculate 0. To make it more visible, let me change the color, some space f prime of 0. I want to calculate it. This, would rather use this. Okay, and they're the same. They said that this, you can use 0 on there. So it's -3 in the numerature. If those are all zeros, it's -3. The denominator, when x equals 0, is -1 squared, and it's actually 1. So the whole thing actually equal to -3. So if it's -3, it's decreasing. So that would be a decreasing interval. Like this. All right, we have to keep in mind what kind of decreasing it is. It's like increasing, then decreasing, right? There's asymptotes, so went all the way up. So right here, you have a local maximum, not an absolute maximum, it's local maximum because you got something like that on the other side of the equation. This looks very similar to the example that we had on the clicker question. So I feel like the behavior is very similar. So right in the middle, we have, this is the increasing and then decreasing. So right here at -1, we had people called, if we call that relative maximum. So we determine that -1 is a point of relative maximum because it went increasing, then decreasing. So those are along the determination increasing, decreasing, we realize we have local maximum right there. There's no local maximum in the middle because you can see later the sign did not change. All right. We go forward right between -3 and between the number 1, 3. For the next interval, we had, let's try f prime of 2. Between 1 and 3, we choose 2 and put in the 2 into this formula. We go 2 minus 1 is -1. And 2 plus 1 is 3, -1 times 3 over 2 times 1, that's 1. The whole thing is -3. That's negative, that means it's decreasing. So that's that one, decreasing interval. And then moving forward in the last interval, let's try 4, f prime of 4. We put in 4 in there, that's 1, 4 in there, that's 5, and 4 in here, that's 4 minus 1 is 3, 3 squared is 9. So that's actually 5 over 9 as well. So that must be increasing because the derivative is positive on the interval, so it's increasing. So that's increasing, decreasing, and then decreasing, increasing to the two parts. Any question? Do we have a local minimum? Right? Decreasing, then increasing. We will have a minimum. So right between this 1 to 3 is decreasing, 3 to infinity is increasing. So right there, in between the decreasing and increasing, we have a local minimum. And it's connected because -1 and 3 is a continuous point. At 1 is not a continuous point. There's a discontinuity. You can see it from our domain. Right, so that finished the entire question. Let's go back to the question itself. The increasing interval are increasing interval is -infinity to -1 and 3 to infinity. Those are increasing interval. The decreasing interval is -1 to 1 and 1 to 3. Those are the two intervals that are the function is decreasing. The relative extrema of the function, we have a relative maximum at -1. We have a relative minimum at +3. And I finished the entire question. Any question? I hope it's kind of clear about what do I do. You can kind of roughly follow the 3 steps. Step 1, we will determine the critical point of the function. Step 2, you identify the interval of increasing and decreasing. Step 3, you will determine. Step 2 is determine the interval. Step 3, for every interval you determine is increasing and decreasing property. That's this example. All right, there's one more example. This one, we have fractions in the power. When the power is fraction, it means root. So whenever you have a root function, if you have a hard time dealing with it, one of the possible way is to convert it into exponential power. And that way we can handle the root better because the differentiation, we need to apply power over differentiation. Find the interval in which the function is increasing, decreasing, identify the relative extrema. So we would do the same as what we did for the first question. If there's anything we have to watch out for, it would be sometime when the original function is well defined, the derivative might not be, because when you apply power to find the derivative, the power would reduce. And for example, this one, the power is x to the 2/3 power. If the 2/3 power minus 1, you have negative 1/3, and negative 1/3 is a division. Whenever we have a division, we have an undefined point. So we would have that kind of derivative that suddenly become undefined, and that may be different for this kind of function. And it's one of the typical situations when we have fractional power. And let's see. This will be our last example for today. And after class, I'll define exercise and homework for this section. All right, so how do we deal with it? The process is very similar. If there's any difference, will be, this is a newer example. We didn't handle root function or fractional power as often as we did with polynomial. So you might have to have a better understanding of the behavior. Now, first we read the function itself. It's right now, this is the power positive, this is the positive power, and the power has a fractional power, but it's a cube root. Now, cube root is well defined for all x value. So the domain will be negative infinity to positive infinity. So we don't have that situation as the previous example where we have to take out point out of the whole number line. Right now, we don't have to take anything out of it. The fundamental meaning of this is actually x to the power 8. The numerator power is a power. The denominator is root. So it's actually cube root of x to the power 8 minus 4 times cube root of x to the power 2. So whenever you have a fractional power, the numerator is a true power. The denominator actually means root. So we have to have some understanding of what's going on, even though we write it as fractional power, but maybe sometimes you have to understand its true meaning. All right, so we're gonna actually keep the original exponential form because it made a differentiation easier. So if you want to find the derivative, we follow the definition. So we would move the power to the front. So we have a over 3 over 8 over 3, and then the power has to minus 1. So we can have 8 over 3 minus 1, which equal to 8 over 3 minus 3 over 3. And now you keep the 3 in the denominator. The numerator is 8 minus 3, which is 5. So then the power is going to be x to the 5 over 3 power. Remember, applying power rule, the power go to the front and the power has to minus 1. So that's the differentiation for the first term. Second term, you're going to move over 4 times 2 over 3. 4 times 2 is 8. So it's going to be 8 over 3. And x to the power of, the power is 2 over 3. But when you differentiate, you have to minus 1. So power minus 1. And that's going to be 2 over 3. Minus 3 over 3. Now they have the same denominator, then you keep the denominator, you subtract the numerator, 2 minus 3 is negative 1. So it's actually negative 1 over 3 power. So that will be the differentiation process. I'm showing the subtraction of the power as clear as possible, just so we can keep in mind that's what's happening. So now there's something we want to take a look. So this is going to be 3 over 8 x to the power of 5 over 3 minus 8 over 3. See what happened? There's a negative power. Negative power means division. So this is 1 over x to the 1/3 power. So that's what the derivative is. So In step one, we want to determine the critical point. What are the critical point? Critical point is when the derivative equals 0 or undefined. Oh, it's already time. All right. So we probably gonna continue from here tomorrow. But you can see once we have that derivative, we're gonna work on how do we set equal to 0 and how do we identify the undefined point. Obviously, whenever x ones are how x equal to 0 is an undefined point. So we do have an undefined point there. And I'll see you tomorrow. Let's continue from here. Bye, guys. I wonder if they want to. Bye.